Hi all, this is Vasu Sham, and welcome again to another episode of Theoretically Podcasting. In today's short solo episode, I'm going to go over a very interesting connection which was alluded to in a previous episode about random walks and supersymmetry, about the more general role that supersymmetry plays, this hidden supersymmetry plays in stochastic dynamics and in the solutions to the Fokker-Planck equation. In particular, we will see how supersymmetry preservation, in the sense that I will define, corresponds to the existence of equilibrium steady state solutions to the Fokker-Planck equation. And when this supersymmetry is spontaneously or dynamically broken, it corresponds to situations where we have steady state solutions that aren't equilibrium Gibbs distributions, but are so-called non-equilibrium steady state solutions. Let's see how far we get, though, and I'd like to begin by just laying out the very basic dynamics of the theory that we're considering. So I'll mostly stick to the mechanical case, meaning that instead of having fields, we're just going to have one-dimensional trajectories involved. So we're going to start with a Langevin-like equation for our field verify. Verify. And this could be a multi-component field, and it's going to be driven by a potential and by a noise term, which is stochastic in nature. So this noise term is going to have the following non-trivial correlation function, and everything else shall be given in terms of this this one type of correlator. So we have Ci, Cj, 2-point function at two different times is going to be proportional to delta ij, knowing about the components, and a delta function in time. So this is a Markov process. Now, following the standard steps of stochastic dynamics, we would derive a so-called Fokker-Planck equation for the probability distribution over verify. So we have P verify T satisfying the equation partial T verify T equals, well, I'll just use the Nabla notation for the gradients with respect to verify. And we're going to have T times. And then we're going to have our force term. So already here we can see that if we wanted an equilibrium solution, namely one for which the left-hand side here vanishes, then what we would do is we would drop this total derivative and say that the gradient of P is proportional to, well, I suppose there's a half here, but we'll basically say that the gradient of T is proportional to 1/2 times gradient of U times P. And then we would solve for P, which would give us e to the power of minus 1/2t times U, and that would be it. That's when we have an equilibrium steady state solution. Interesting things happen when we're prevented from doing so. But I would like to not start from here, but develop instead a path integral describing the dynamics of the trajectories, the ensemble of trajectories that we have here, and then describe how we can derive a Lagrangian for that path integral and a Hamiltonian, which will connect back to this Fokker-Planck equation. So we start by describing the partition function over the noise as being given by a Gaussian integral suppose there's a 2. Now, there's a standard set of manipulations which will actually reveal the hidden supersymmetry I've been alluding to, starting from here. And very briefly, I did touch upon this in the previous episode having to do with the random walks, where we were looking not at a system involving time derivatives, but basically a Langevin equation where this left-hand side was zero. It was just a relation between u and c, so it was basically an ordinary integral instead of a functional integral. And we did look at an example of how the supersymmetry of that setup could be broken. But here we'll look at this in the context of this one-dimensional model, or yeah, this many-component one-dimensional field theory, and we will find out how how this relates back to our traditional notions of the Fokker-Planck equation and so forth. So here, what we employ is the Faddeev-Popov trick, which is that if we were to take a functional delta function, um, then we have a resolution of identity given by the following. Um, in our case, we're going to take the delta function to be the one that enforces the Langevin equation, and we're going to take our variable alpha to be var phi. So what we're going to do is insert this resolution of identity back into our partition function. So the noise partition function, with respect to which we compute noise statistics, and that is the origin of all the statistics in the system, right? So per noise, there's one trajectory that solves the Langevin equation. We'll put a flag there. Perhaps there's one, perhaps there's more, perhaps there's none, but we'll get to that. Ideally, there's one, and what we're going to do is we're going to look at the following insertion of identity. And now the determinant, the all-important determinant, is going to be of the form well, I will just write down the explicit form of the functional derivative. So we're going to have partial t delta ij minus nabla I nabla I j u. Great. And then there's a delta function with respect to time, which is implicit in this. So this is a bit of a schematic representation. When you write it in terms of Gauss, as in Grassmann variables, it'll be more explicit. So you can see where we're going and how we're going to eventually land on the Gauss. All right. So now what we're going to do is use up the delta function, and we're going to get that this delta function sets these x's to phi plus grad u, right? So what we're going to have is that there's now just the integral over var phi with the determinant that comes along for the ride. And we're going to see that we have the exponential of dot var phi I plus nabla var phi I u squared. All right. So now this comes with a minus. Well, yes. 1 over 2t. Now what we can do is, before proceeding further, note that the expansion of the whole squared of dot var phi I plus nabla actually contains a total derivative term, especially when you put it under the integral sign, which is what we should be doing here too. Apologies for, yes. So to put it under the integral, then we basically have the dot verify I squared term, and we have the nabla verify u squared term. And then we have a term that we basically can drop because it's the total derivative. So it's 2 times dot u. No, because we're going to have phi dot nabla phi u, which is nothing but u dot. And we're just going to drop that term. So under the integral sign, we're just going to drop it. We're going to assume that u satisfies the right boundary condition in time, so as to allow us to write this as a sum of squares. Well, let's write this as I. Okay, and now we have something shaping up to be a nice action, and we can use it up here. While I plug this in, I shall simultaneously exponentiate this determinant by introducing 2 sets of Grassmann fields, psi and bar psi. And we have in our action now we have our newly gotten action, and we have now a term that looks like the following. So let me just remove this bracket, put it here. Looks like bar psi I, and you're going to have partial t psi I. So this is a nice kinetic term. And in addition to that, what we're going to have is minus bar psi I, nabla I, nabla j u psi j. Perfect. So we have an action involving both bosonic and fermionic parts. And from this generating function, we're going to bounce back. We're going to bounce back to a Hamiltonian. And just by looking at this, we can tell that we're going to have a kinetic term minus potential term type Hamiltonian here. So this is like minus a potential term, so we're going to have plus the potential term, just to be given by the square of the gradient. And in the fermionic sector, this will be the only thing that contributes to the Hamiltonian, because it's already of the form P dq. Right? So PQ dot minus H. So H is basically just going to be given by this. But if you were to write this as an operator, we're going to have to introduce a momentum conjugate to phi, and we're going to have to introduce conjugate pairs of fermions. And so the structure of this Hamiltonian is going to be the following. It's going to have the square of this going to have the square of this, right? And then it's going to have So here there's a bar misplaced or a bar gone too far. This is what I want. So you have a kind of fermionic Hamiltonian that looks like this. So you have A dagger, I, A, J. Well, it's a big. That takes care of the structure of these two terms when we write it in terms of fermionic raising and lowering operators. And what's very fun about this system is that there's a fermion number, A dagger A, which commutes with this entire Hamiltonian. And so we can basically split up the Hamiltonian into its action on each of the fermion number like the fermion number eigenstates. And we will see this analysis clearly in the following reference, which is a very nice reference titled On the Hidden Supersymmetry of Fokker-Planck Equations with Potential Forces by these gentlemen from the Landau Institute back in '83. And they basically consider the generalization of what I was looking at to the case where you have fields that depend on space in addition to time. But much of the analysis carries over. They have this kinetic factor in addition to the T that I had. And what they do is they develop the so-called Martin-Séguier-Rose path integral, which is, well, very much the same as what we were describing before. And at the end of the process, they show that, well, they have the following Hamiltonian, which is much the same as what we had, or they have the following Lagrangian, which is much the same as what we had, and they arrive at this Hamiltonian, which is also similar to what we had. And note that they have space dependence, but they're keeping one component of phi. I'm considering the case where there are many components, and that's another difference. And anyway, they proceed with the analysis to say that starting from 19, we can basically look at the total fermion number, A dagger A, integrated over dx, because they have a space dependence now, that this commutes with the Hamiltonian. And so the Schrodinger equation corresponding to this Hamiltonian splits into independent equations for each n. Now, interesting things happen when we look at the zero and maximum values of n. And so let's take the case where we have the zero eigenvalue. And in that case, we have A acting on psi minus equals 0 for all x. For us, there's no x, so it's just A acting on psi minus equals 0. And there we have H minus, which is basically given by a simple transformation involving this exponential factor of the solution to the forward Fokker-Planck equation, which is what we wrote down at the very beginning of the notes, right? Now, in the case where n equals n max, it's very interesting. What we have is a wave function satisfying A dagger psi equals 0, and then the Hamiltonian is basically similarly related to a solution of the backward Fokker-Planck equation. So we basically take the forward and backward Cramér-Moyal expansions and then truncate to the second order and take the small time step limit, derive the Fokker-Planck equations. There's a forward and backward Fokker-Planck equations that are related basically by a change of the sign in front of the second derivative term, which knows about the fermions. And the rest of the equation is the same. And this is what they base their analysis on. The analysis specifically of the structure of the ground states. Now, H hat actually, due to a supersymmetry that's inherent in the system, can be written as the square of a supercharge. What is that supercharge? Well, it's basically given by minus t pi phi, right? The momentum conjugate to phi plus the gradient of phi a plus term proportional to A dagger with the opposite sign between these two terms. Very interesting structure because it's exactly the kind of thing that one would peel away in the equilibrium analysis to find a solution to the equilibrium Fokker-Planck equations. And that's exactly what it means to look for ground states. So they say, look, we can use the equation cube psi equals square root E psi for the derivation of the spectrum and wave functions of this theory. In particular, if we're looking for ground states, we can use the equation cube psi equals 0 and note that it has two formal solutions, right? Where you have an exponential of v over 2t times states psi plus minus that are determined by either A minus equals 0 or A dagger plus equals 0. And if one of these wave functions is normalizable, then that's the true ground state solution, right? That's the equilibrium probability distribution. In other words, the equilibrium Gibbs state. However, if there's a potential where both of these are not normalizable, then this equation doesn't have true solutions, and so E naught, the lowest eigenvalue of the Hamiltonian, is positive. That means the supersymmetry is spontaneously broken, right? That corresponds to having non-equilibrium steady-state solutions. Now, there's yet another situation where there can be so-called dynamical breaking of the supersymmetry. And to see where that can happen, we'll jump to a very nice reference of Witten's, where he studies dynamical supersymmetry breaking in the context of just supersymmetric quantum mechanics. Note here that they comment on what happens when we have only one component, right? So if you have only one variable phi instead of the field phi x, in other words, if you have just one component of phi, then the set of states would just be psi plus and psi minus. And that would be the case with supersymmetric quantum mechanics. And so here we have section 6 of Witten's classic paper on, it's a big paper, dynamical supersymmetry breaking from 81. So this predated the analysis involving stochastic dynamics. But if we go back to the simple model, I mean, this is a wonderful paper to read. It has a lot of other sections involving field theories, but to keep it simple, let's just look at the case with quantum mechanics. So here, what Witten wants to do is look at a model involving just supersymmetric quantum mechanics, where there are these operators Qi commuting with the Hamiltonian, satisfying the following algebra. Now, this is like the multi-component case involving multiple phi i's that we were discussing in the Fokker-Planck situation. In the case where n equals 2, that corresponds to having just one phi, there's just one spin half particle moving on the line because this is one-dimensional. And basically, there's this two-component polyspinner used to write down the structure of the Hamiltonian. And note that W here is grad U in our notation, so that in the Hamiltonian, what appears as the second derivative of U in our notation becomes dW dx. Great. And so what we call U will be the integral of Wx with respect to x, right? Okay. So the assumption here is that W goes to 0 as x goes to infinity, so the spectrum of the Hamiltonian is discrete. And now Witten asks, well, what are the conditions under which the supersymmetry is spontaneously broken? Now remember, when the supersymmetry is preserved, it's perfectly fine. We use the usual trick, and we can basically solve for our equilibrium probability distribution. Here we're looking at situations where we cannot. And one of them was already alluded to in the previous reference, when we have spontaneous supersymmetry breaking. And the spontaneous supersymmetry breaking case corresponds to one where we have a potential doing the following, right? And so here, see, W has no zeros, and supersymmetry is spontaneously broken at the tree level, right? So we don't really need to do any analysis. Here, there's a passage where Witten considers the situation where we just look at order H bar corrections to the vacuum energy. And there's basically a sense in which there's a protection of the ground state energy under radiative corrections, which is very similar to the general supersymmetric protection that observables in field theories enjoy. And so that's what Witten comments on here, saying this is an example of the famous cancellation between Bose-Fermi contributions to the ground state energy of supersymmetric theories. That's another reason why, for instance, the cosmological constant is something that a positive cosmological constant is something that supersymmetry doesn't quite like either. And anyway, then we basically see that instead of looking at higher terms of perturbation theory, we can just look at the exact spectrum of the theory, and we'll see some very interesting effects. Okay, so at the tree level, the number of supersymmetric states equals the number of zeros of W. That is grad U, right? And in the exact spectrum, the number of supersymmetric states is equal to 1 if W has an odd number of zeros, and 0 if W has an even number of zeros, right? So this is an important count, right? So here he says, if you take something like 7a, right? So it's w squared and this is w, right? W cuts the origin once. W squared is purely convex. So there's just the exact ground state that's supersymmetric. In figure 7c, as we discussed, it's spontaneously broken. That is, the lowest eigenvalue of the Hamiltonian is actually one with positive energy, strictly positive energy. Now, 7b, right, where we have W cutting the axis like this, and the potential W squared forming this dashed line, right, a double well potential, right? So it's just a double well potential in supersymmetric quantum mechanics. That's the situation that Witten's talking about here, right? So here he says there are non-perturbative effects that dynamically break the supersymmetry, which is unbroken at the tree level. And so you see, the equation q psi equals 0 must be satisfied by a supersymmetric state. And because the general relation q squared equals half h, you can show that satisfying q psi equals 0. So basically, h equals 0 is the same as saying the q psi equals 0. And this equation is sigma 1 p psi equals sigma 2 w psi, right? So this is just a Pauli version of seeing the relation that we had in our previous notation, where q was formed from gradient with respect to phi and du d phi. And now, with some tricks, right, you multiply by sigma 1 and you use the Pauli algebra, use the SU2 algebra of Pauli matrices, you find that d psi dx equals w times sigma 3 psi fx. And the solution is psi fx is the exponential of the integral of w sigma 3 acting on psi of 0. This is just the exponential of u in our notation, because we have u, which is given by gradient of w. Now, here's the caveat. This defines a supersymmetric state, provided psi is normalizable, right? And now, if w has an odd number of zeros, then the sign of w for x going to infinity is opposite from the sign of w as x goes to minus infinity. In this case, there's a unique choice of psi of 0 that makes 31 normalizable, that makes this normalizable. If w goes like x cubed, then for large x, we basically have that this is a quarter x to the power 4. And if sigma 3 psi 0 equals to minus sigma 0, then 31 is normalizable, right? Now, situations that are interesting arise when w has an even number of zeros. Then the sign of w is the same for when x goes to plus or minus infinity. In that case, there's just no choice of psi of 0 that makes 31 normalizable, right? So if w is like x to the 4, then for large x, this integral, in other words, u, goes like x to the power 5. In this case, sigma 3 psi 0 equals minus psi 0, then 31 behaves very badly for large negative x. And if sigma 3 psi 0 equals plus psi 0, then 31 behaves badly for large positive x. Thus, we find that both in 7b and c, where w has an even number of zeros, 2 or 0, because, when we have spontaneous supersymmetry breaking, we just have no zeros. We just raise the potential. Then the exact spectrum does not contain a state invariant under the supersymmetry. And so you can have a classical spontaneous breaking of the supersymmetry, or you can have an interesting situation where in the quantum theory, because of w as in the gradient of u, having an even number of zeros, we have dynamical supersymmetry. And the dynamical supersymmetry breaking comes from non-perturbative effects. So it basically comes from the fact that you can tunnel between these two vacua, right? And these tunneling effects, these instanton effects, break the supersymmetry. So the tunneling rate is a contribution that basically breaks the supersymmetry of the model. And that is a very interesting and neat phenomenon. And that too is commented on in this classic paper of Parisi and Sorlas. So this is a different Parisi and Sorlas paper than the one that I was describing in the case where we were looking at random walks and talking about supersymmetry. Here, this is the one that you probably hear about more. It's a little bit more famous. It's like when people talk about Parisi Sorlas supersymmetry, they're really referring to this paper. And this one is from 82. So it's quite close on the heels of the dynamical supersymmetry breaking story of Witten's. Here they consider a very similar toy model to what we discussed in the case where we had the random walks in supersymmetry, where we don't have the phi dot term and we just have the following Langevin equation. And they basically describe what the ward identities corresponding to this system and its emergent supersymmetry are going to be. The action in this case has no phi dot term, so just has gradient u squared. It has psi bar times the second derivative of u psi, right? And the supersymmetries just take the following simple form, and through them we can derive the following ward identity, right? Ux psi equals psi psi bar, right? And here they discuss the different situations where we can break the supersymmetry as well, right? And those situations arise when either this equation has no or too many solutions. Ideally, if it just has one solution, then what happens is that the statement that the ground state energy is 0 is the same as saying that this partition function is normalized to 1, right? And that all works given the tricks that we did at the very beginning of this episode, provided that this equation really just has one solution. It's easier to look at the case where it has too many solutions, which is what they describe here. So say this equation has n of eta solutions, with n of eta being greater than 1. And from the stochastic equation point of view, what we would do is define noise averages using the following expression, right? And so epsilon is +1 for every I. In the present case, what we're going to see is the following expression. And what's going to happen is that when we use up the eta integral, we're going to get a sum. Because there's multiple solutions, we're going to get a sum of determinant divided by the modulus of the determinant for each I, right? And what is that going to be? That's going to become a sum over the sign of the determinant, right? So normally we would use the eta integral, we'd just plug this back in here and everything would be great. Here, that's not what's going to happen. We're going to do the phi integral instead. And then doing the phi integral is going to give us this sum over determinants just from using the definition of the functional delta function. And so we've kept eta, we've eliminated phi. It's the opposite of what we would normally do, where we would keep phi, eliminate eta. And that makes things nebulous, right? Makes things mysterious, whereas here it's quite clear what we should be doing. And so this is basically what breaks the structure of this theory. It basically breaks this the situation where the integral over this should give us 1, right? So equation 1.11 is not valid anymore. Well, let's go. So this is the definition 4.7. Equation 1.11 are these two conditions, right? So these two conditions that tell us how to compute averages, right? By just sticking f into this action. Here, there's going to be an additional sum, and that makes it a little bit more tricky, right? And so that definition is no longer valid, and so we can't take the implication of how we get 1 from this normalization condition anymore. Could always change the average by making this substitution, in which case you could not break it, but then they're saying, well, the only way is like if you have n of eta always equal 1, then there are no options, and so supersymmetry cannot be spontaneously broken in that case. And then you can look at the case where this equation has no solution. So one such situation is when you have u plus infinity equals a, u at minus infinity, the gradient of u, equals b, and gradient itself is monotonous in phi. And so for eta greater than a or less than b, there are no solutions. Then what happens is that you see this integral really can only equal 1 if a goes to infinity and b goes to minus infinity. If one tried to work out the ward identity, then we'll see that the ward identity is basically violated by a term that knows about e to the b minus b squared over 2 and e to the minus a squared over 2. And again, when these go to infinity, that's when the ward identity will be satisfied. This violation of the supersymmetry is exactly the one that we described involving the fermionic zero modes and so on in the previous episode about random walks in supersymmetry. Now, Parisi and Surlas also comment on the model that Witten considered. So they go through the very similar steps that we did, drop this term, and they obtain the Hamiltonian system that we were describing. And basically, they say that at t goes to infinity, the behavior of P is governed by the lowest eigenvalue E naught of H. And then they say that, well, nice equilibria are when E equals 0. But here they again go back to the case where there's a possibility of dynamical breaking. So here their U is like RU, so you take the gradient in order to actually form what Witten was calling W. So the odd and even roles are switched because there's one gradient involved. So when n is odd, they say that for large n of t, the probability is concentrated at x equals minus infinity and is zero everywhere else, which means that the stochastic equation won't have solutions for most eta. So it's the same kind of phenomenon, right? And so that's why supersymmetry is broken, right? And if n is even, then p is more evenly distributed and supersymmetry is not broken. So this odd and even role has been switched because Witten was talking about the gradient of the quantity that we have here. Here we're talking about the quantity itself, right? So this is in agreement with Witten's analysis, which was the year before this paper came out. So it was fresh in their memory. So in summary, what's very interesting is that when we map stochastic systems to a supersymmetric quantum mechanical system, then what we find is that the preservation of the supersymmetry is equivalent to there being equilibrium steady state solutions. And when the supersymmetry is spontaneously broken, then what we have are non-equilibrium steady state solutions. And these are immensely interesting. And I think some of their properties are still being worked out as we speak. I saw a paper from just this year where they talked about the emergent second law of thermodynamics for such systems. And that'll be fun to get into in a future episode. For now, thank you for listening. If you like this, please like, subscribe, comment, share, and I'll catch you next time on Theoretically Podcasting. Bye bye.